morning, ladies and gentlemen. Let's continue our discussion of logarithms, shall we? And in this lesson, what we'd like to do is to concern ourselves with products and quotients of logarithms and of numbers. And let's approach this from an idea that we are quite familiar with, in which suppose we looked at 10 raised to the logarithm in base 10 of a. And what have we said that this is equal to? Right from the definition, and Tim?
A.
This then is equal to a, and similarly, suppose we had 10 raised to the logarithm in base 10 of b. We know that this is equal to
B.
what?
B.
Is equal to b. Now let's look at this number a and b, and if we then were to multiply them, we then would certainly have 10 raised to the log of a times 10 raised to the log of b. And here we have two numbers of the same base, and what can we do with those exponents but to add them? Therefore, we have 10 raised to the log of a plus log of b. All right? Now, but what do we know about 10 raised to the log in base 10 of a times b? What do we know that this is equal to? But what?
AB.
This is equal to a times b. Therefore, substituting this name for ab in the line above, we have 10 raised to the log of ab is equal to, and right here that's then 10 raised to the log of a plus the log of b. And if we have two numbers with base b, if b to the x sub 1 is equal to b to the x sub 2, what then is our conclusion about x sub 1 and x sub 2? And we have already said, Doug,
They're equal.
that they are equal. Therefore, in fact, we may write this as the logarithm of ab is equal to the logarithm of a plus the logarithm of b. And in fact, we may even state this as a theorem, and the restrictions on a and b are what? For values of a, which are all real numbers, which are what? We know that they must be greater than 0. All right? What do you think we may say about the logarithm of a divided by b? And just by the analogy of what we have done, Doug,
The log of A minus the log.
this is the log of a minus the log of b. And again, for values of a which are greater than 0 and b which are greater than 0. And in fact, we may also state this as a theorem. All right? Now, let's utilize these theorems in some computation. And here we have a problem in which it says compute the product of these two numbers by logarithms. Well, let me call this number p, whatever that product is, 47.38 times 0.3784. All right? Now, what I'd like you to do is to get into the habit of estimating that number, whatever it happens to be. All right? And we've already done this, and that was the reason why we did it, actually. And 47.38 is about what? 5 times 10 to the 1. And here we have 0.3784 is about what? 4 times what? 10 to the negative 1. And looking at this, 5 times 4 then is 20 times 10 to the what? 10 to the 0 power, which we know is 1. Therefore, approximation is equal to what? Is equal to 20. All right? Now, there is another habit that I would like you to get into, and that is to actually write down what you would like to show. Namely, that the log of p is going to be equal to the log of 47.38, and that's times 0.3784. 3784, and now our theorem tells us that this then must be equal to what? The logarithm of a times b must be equal to, and Doug?
The log of A plus the log of
The log of a, which is 47.38, plus the log of b, which is 0.3784. All right? Now, in fact, I'd even like to write this down as sort of a 3-step procedure. The first step is to estimate what the number is. The second step is to write an equation using the theorem that you have. And the third step that I would like to set up is a pattern by which you can actually find this number. And the pattern that I think here bookkeeping becomes an important idea in order to be able to make sure that you get the correct result. Accuracy here is quite important. Now here we have the log of this number is equal to something, and notice I'll write all of this down before I actually begin to look anything up in tables and do any computation. We're going to add these two, and this plus sign reminds us of that. Perhaps you don't need to get into that habit, and that then is going to give us the logarithm of p, and then the anti-log of that number is the number that we want, namely p itself. Is that right? Okay. Now, looking here, we see that the characteristic must be what number? 47.38 has a characteristic of
1.
Of 1 point something. Here we have point 3784 has a characteristic of negative 1, which we would rather write as 9 point something minus 10. All right? I've already looked these numbers up in the table before the lesson started, and if you don't mind, rather than our taking the time now to do all of this computation, notice also that this number 4738 involves interpolation, and I've already done that interpolation, and this number turns out to be 1.6756. Similarly, the logarithm of 0.3784 turns out to be 9.5779. Now let's actually go ahead and do our addition, in which here we have negative 10 plus 0, so to speak, is negative 10. 9 plus 6 is what? Here we have 15, there we have 13, 15, 12. Now notice here, 11 plus 1 is 12, and simply carry that 1 because these are positive numbers that we are dealing with, and 9 plus 2 there is what? Is 11, is that right? And we have then 11.2535 minus 10. But that we know is a characteristic of 1. All right, now we want to look at the log of p is 1.2535, and I've already done that anti-log, and the number turns out to be 1793. And therefore, where must my decimal point be in order to give us the correct answer, Peter?
17.93.
17.93, and sure enough, looking back at our estimate, which was the number 20, I think you will agree that, that this would be correct. Notice also that the number of significant digits that we started with in our problem was 4 in each case, and in fact our final result can be no more accurate than the number of digits that we started with, all right? And so we may think of this in terms of 17.93 with 4 significant digits. Well, let's look at another problem. This time, let's do a problem that involves division. And we would like to compute. Notice I've taken the same numbers, but this time I have negative 0.3784. All right? Now, what we need to do is to, well, let me call this number q is equal to some number. And in this case, 47.38 divided by, now we know that if I were interested in the logarithm of q, where we have a negative number there, positive divided by negative is negative, the logarithm of a negative number is what? It's undefined. So let's then take the absolute value of q, and then over here we will have simply what? 0.3784. Okay? Now again, let's estimate. An estimate of the absolute value of q is going to be equal to what? And here this is about what? 5 times 10 to the first divided by, and this is about what? 4 times 10 to the negative 1. Now 5 divided by 4 we know is approximately what? Well, we know that it is 1.25 times, now 10 to the 1 divided by 10 to the negative 1 is 10 squared. And now we have there a number which is what? 125 is our approximation, our estimate of the product q. Okay? Again now, thinking of this as our first step procedure, our second step then is to talk about the logarithm of, in this case, the absolute value of q is going to be equal to the logarithm of the numbers that we are dealing with, 47.38 divided by 0.3784. And our theorem tells us that this then must be equal to what? The log of 47.38 minus the log of 0.3784. Good. Now, in our third step, what we would like to do is to simply set up our procedure before we actually look anything up in the table, all right? Now, I really want to insist on this because I think it's going to help you prevent mistakes. And then the logarithm of 0.3784 is equal to some number, and our subtraction symbol reminds us that we are going to subtract. This then is the logarithm of the absolute value of q, all right? I don't need all those parentheses. And then, in fact, if I wrote the absolute value of q as our antilog, and then we will interpret q in terms of the original problem, which we know is going to be what kind of a number? It's going to be negative. Well, again, let's look at these numbers. We've already said what the log of 47.38 is. It has a characteristic of what? 1 point, and what is it? It is what? 6756. 0.3784 is what? Characteristic of? 9 point something minus 10, where that something is what? The mantissa is 5779. Now notice, I purposely selected this example so that we now want to subtract, but now I have to subtract 9 from 1, so to speak, and indeed, because this number is positive here, we really can't then handle that with respect to our characteristic. Now, the easy way out of this is to simply look at this number of 1, a characteristic of 1, and give me another name for that number 1. Charles? 11 minus 10. Very good. Now let's go ahead and proceed as we normally subtract. Negative 10 from a negative 10 is 0. 9 from 16 is what? 7. 7 from 14 is 7. 7 from 13 is what? From 16 is 9. 5 from 5 is 0 point, and 9 from 11 is ordinary subtraction, which is 2. All right, now we're interested in the antilog of 2.0977. I've already looked that number up in our table. It turns out to be 1252. And again, here this would require interpolation. And now looking at our characteristic of 2, our final result, the absolute value of q is what number? And Kirby?
125.2.
125.2, but since one of our original numbers was negative, our final result then is going to be, Kirby?
The opposite of 125.2.
Which is a negative 125.2, and that's our final result. Again, I want to insist on this 3-step procedure to estimate, to actually write down a sentence using your theorem, and then this little bit of a chart or a table or an algorithm in order to help you with the solution. Well, let's look at a fourth problem. Here it says find the solution set over R of this equation. And notice for the first time we hope that we can solve an equation that involves this logarithmic function. Now, on the left-hand side, it's the log of A plus the log of B, and our theorem tells us that this must be equal to what? The log of A times B. So we have there the log of x plus 1 times an x minus 2 is equal to. Now notice this is in base 10. And on the right-hand side, we have the log in the base 8 of 8. But what do you know about the log of base 8 of 8? It's equal to 1. Give me another name for 1 in base 10. Log in base 10 of 10. Very good. So let's write this as the log in the base 10 of 10. Now we had another one of our statements which said that if the log of x sub 1 is equal to the log of x sub 2, therefore what must hold true? But that what? X sub 1 is equal to x sub 2. Is that right? Therefore we may say what? That we have x plus 1 times an x minus 2 is equal to 10. And now let's see, here we have x squared, and there's what? Minus x minus 2 is 10. We have x squared minus x minus 12 is 0, and you hope that you can factor this quadratic equation. We have x times x is an x squared, and what then do we see, Bill?
X minus 4, x plus 3.
X minus 4 times an x plus 3 then is a negative 12 and an opposite of x. Therefore, using one of our theorems, x must be equal to what? X is equal to 4, or x is equal to negative 3. Now, let's go back to the original sentence. When x is negative 3, we have then the log of negative 3 plus 1, which is negative 2. And what then holds true? What can you say about the log of negative 2? Undefined. Therefore, this value of x cannot be in our solution set. And indeed, if you were to check the positive case, the log of 4 plus 1 is the log of 5, plus the log of 4 minus 2 is 2, and that then is the log of 10, which indeed you know is 1. Okay? So the solution set in this case is the one number 4. let me give you your homework assignment in which you can practice some of these problems. And indeed,